Hi everybody, my name is Aman Arora and I'm a PhD student at UT Austin. I'm excited to share our work to create a deep learning benchmark suite for FPGA research called Koios. This was a collaborative effort involving students and advisors from 3 universities, and I want to take this opportunity to thank everyone involved for making it happen. Let's get started. The standard flow for exploring FPGA architecture and CAD tool improvements looks like this. We create a description of the FPGA architecture we are trying to explore. We take a set of benchmark designs. These benchmarks should reflect the application domain that we are trying to optimize the FPGA architecture for. A CAD tool takes these benchmarks and synthesizes, places, and routes these benchmarks for the provided FPGA and generates reports that contain area, frequency, and power metrics. By comparing various metrics from these reports for various architectures, we can identify the architecture that satisfies the requirements that we have. Benchmarks play a vital role in this process because using wrong benchmarks can generate wrong results. Deep learning has become a very important workload for FPGAs in the last decade, and many new DL-optimized architectures have been explored, proposed, and deployed. Some of the recent products from the industry include Intel TensorBlock and Xilinx AI engines. There have been some works from the academia as well, like Tensor Slices and NVRAM Compute. We need the right benchmarks for performing FPGA architecture exploration for DL-optimized FPGAs. If we look at the existing FPGA benchmark suites, we see that some of them have small designs, some of them have designs that are not heterogeneous, many of them do not go through open source CAD flows, and none of them are DL specific. Using these current FPGA benchmark suites for DL specific research means that we might be optimizing for wrong targets. And in absence of representative benchmark suites, what ends up happening is that researchers create their own custom benchmarks for each individual study, which involves a lot of effort, first of all, and secondly, that makes comparing results from various studies almost impossible. Koios solves this problem. So what is Koios? Koios is a DL-specific benchmark suite for FPGA research. It has 19 benchmarks that cover a diverse representative space, and we will look into this space in more detail. It is open source on GitHub, and it works with VTR, which is arguably the most common FPGA research framework out there. It contains original designs that we've coded and designs that we have recreated from prior industrial and academic works. And we believe that it is suitable for DL-specific architecture exploration and CAD research. So let's look into some more details about the Koios benchmark suite. This slide shows a list of all the benchmarks that are available in this suite. I know this is a long list and there is a lot of words here, but don't worry. In the next few slides, I'll take you through the composition and characteristics of Koios. We will look at the benchmarks from these 6 angles or viewpoints, and hopefully by the end of this section, you'll have a good feel of the diversity and composition of Koios. Let's start with design size. Koios has benchmarks ranging in size from about 11,000 primitives to 1 million netlist primitives. Some of these designs have multiple variants, large, medium, small. Why do we need to have designs of multiple sizes in the benchmark suite? Because large sizes pose an interesting, challenging problem to CAD tools. However, smaller designs can be used for early stage experiments because the turnaround time is shorter. Let's look at implementation style. The benchmarks in Koios are all written in Verilog. Some of them we hand code directly in RTL. However, some of them were generated using HLS tools. Why use HLS tools? HLS is becoming very common these days, first of all. And secondly, HLS tools generate code that have some special characteristics like widely distributed control signals and complex state machines. Koios has designs from both types of implementation styles. The next angle is target neural network. Koios has designs from all major classes of neural networks: multi-level perceptron, convolutional neural networks, recurrent neural networks, reinforcement learning, and some designs that cater to multiple neural network classes. It is important to include different classes of neural networks because different classes have different compute and memory requirements, which reflects in the different resource breakdown of these designs. Let's look at Koios from an acceleration paradigm point of view. There are three major acceleration paradigms that are used for accelerating DL workloads using FPGAs. The first is software programmable overlays. These are designs that can execute multiple DL models without needing to reprogram the FPGA. These designs have complicated control logic typically and a generic data path. The next acceleration paradigm that FPGAs use are custom network-specific architectures where a DL model is directly mapped onto the FPGA. So these designs have hard-coded control and data path that work for that specific network. The third acceleration paradigm is layer-specific accelerators, where one or two layers are accelerated on the FPGA and the rest of the network executes on a CPU host. These designs typically have no to little control logic and mostly data path. And we have included designs from all these three acceleration paradigms in Koios. Numerical precision. Custom numerical precisions are key for deep learning workloads. Common precisions used in deep learning include binary, different size of integer or fixed point, bfloat16, and IEEE FP16. We have designs from various precisions in Koios. Including designs of different precisions helps explore new DSP and VRAM architectures. Circuit properties. Different circuit styles exercise CAD tools in different ways. Some common circuit properties or styles that are common for deep learning designs include regular structures like systolic arrays, large induction trees, and long cascades of hard blocks. And we have designs in Koios that cover these different architectural styles. Let's move on to the next section where we look into our methodology. How did we go about curating this benchmark suite? To begin with, we selected designs keeping representativeness and diversity in mind. Then we implemented these designs and did some basic functional verification on them. After that, we modified the designs to ensure compatibility with VTR flow. This involved removing Verilog constructs that were not supported by VTR, removing vendor-specific IP cores, etc. And then finally, we ran experiments to ensure the suitability of these benchmarks. These involved comparing them with existing benchmarks and running some case studies. We used the latest version of VTR for our experiments. In order to gain insights on different properties of these benchmarks, we compared Koios with VTR benchmarks, which are non-DL and the only benchmark suite that are available that use open source CAD flow. To run our experiments, we created an FPGA architecture which is very similar to a modern island-style FPGA, where blocks are laid out in columns. Logic blocks contain fracturable 6-input LUTs. Block RAMs are 20 kilobits in size. The DSP slices here are complex. They have modes that include low precisions like fixed point 9-bit and floating point 16-bit. And then we have IOs on the periphery. Okay, let's look at the results from our experiments. Here is a table that shows the various properties of these benchmarks like resource usage, frequency, and routed wire length. I know there is a lot of numbers here, so I'll walk you through the important points. First thing we see is that these designs are very heavy on DSP and VRAM usage. Then we see that frequencies range from about 64 megahertz to about 300 megahertz. These frequencies are actually much higher than those for VTR benchmarks. Then we see that for routed wire length, there is a correlation between design size and routed wire length. As the designs become smaller, the routed wire length becomes smaller, which is also intuitive. Okay, let's compare Koios benchmarks with VTR benchmarks. In this scatter plot, we are plotting VRAM to logic block ratio on the x-axis and DSP to logic block ratio on the y-axis. So going to the upper right side in this chart means higher DSP and VRAM density. Right off the bat, we see that the red star, which is the average for Koios benchmarks, is more to the upper right side compared to the blue star, which is the average of VTR benchmarks. The other thing that we see is the spread. We see that the Koios benchmarks have designs that are very VRAM heavy and some designs that are very DSP heavy and everything in between. On the right side, we are showing a scatter plot that has adder to LUT ratio on the x-axis and flip-flop to LUT ratio on the y-axis, which means as we go to the upper right side, the flip-flop and adder density increases. Now we can see that along the y-axis, the red star is up compared to the blue star, which means that the Koios designs have higher flip-flop to LUT ratio, but on the x-axis, the red star is behind the blue star, which means that Koios benchmarks have lower adder to LUT ratio, which was surprising to us. And that turned out to be the case because there was this outlier design in the VTR benchmarks, which had a lot of adders in it. If we remove this specific design from the average comes down for VTR benchmarks, and it turns out that Koios benchmarks actually have about 1.2x the adder to LUT ratio compared to VTR benchmarks. Now let's look at some average and range charts to compare VTR benchmarks with Koios benchmarks. This chart shows us that Koios benchmarks have a much wider range of number of netlist primitives compared to the VTR benchmarks. We see a similar trend for number of near critical connections. This is important because this tells us that Koios benchmarks pose a much more challenging optimization problem to the CAD tools. And thirdly, we see that logic depth for Koios benchmarks is much smaller compared to VTR benchmarks, which tells us that these designs, the Koios designs, are highly pipelined and run at higher frequency compared to VTR benchmarks. Okay, let's look at an architecture exploration case study that we conducted to look at the effectiveness of Koios benchmarks for DL-specific research. In this case study, we varied the hard block to soft logic ratio of an FPGA architecture. We started with the baseline architecture where every 8th column was a hard block, which is either a BRAM column or a DSP column. Then we created a denser version of the architecture where every 4th column was a hard block, and a densest variation of the architecture where every 2nd column was a hard block. We then plotted the frequency and total routing wire length for each benchmark suite across all the benchmarks in that suite averaged across multiple seeds. We saw that in going from baseline to denser to densest for Koios, the frequency increased by 8% and the total wire length reduced by 17%. This was intuitive because the Koios designs are very DRAM and DSP heavy. But with VTR benchmarks, we see that both frequency and wire length got better from baseline to denser, but then degraded in going from denser to the densest variation of the architecture. This shows that using DL-specific benchmarks can help reach right conclusions to identify DL-specific or DL-optimized FPGA architectures. And the takeaway here is right benchmarks, right conclusions. Okay, let's conclude this talk now. We have released a set of benchmarks called Koios that are suitable for DL-specific FPGA architecture and CAD research. Koios benchmarks are open source, representative of contemporary DL workloads, and work with the popular VTR open source framework. We have started using these benchmarks for our studies, and we invite the FPGA community to use them, report bugs, and contribute to them if possible. We encourage and welcome contributions to these benchmarks. Thank you for tuning in. Here is the link for these benchmarks. Thanks again. Bye-bye.